In this video, we are going to discuss a special type of oscillation, which we will call simple harmonic oscillation or simple harmonic motion, or simply SHM. Let us first start with an example of simple harmonic motion. You can see in the picture that a spring is attached to some support here, and the other end of the spring is attached with a mass. Now, if we pull or push this mass along this line, it will start to oscillate. And if this plane on which the object is resting on is frictionless, well, then we can say that this motion of this object is a simple harmonic motion. Actually, this can be considered an example of simple harmonic motion if the displacement from the equilibrium position is very small. So now let's find out the condition for simple harmonic motion by analyzing this problem. So first, let us ask, what are the forces that is acting on this system? Well, clearly you can see that it is moving along this plane, right? The horizontal one. That means the vertical forces must be zero. And it is, because the weight of the object is acting downwards and the normal reaction of the plane on the object is acting upwards. Okay, so the both are equal and cancel each other out. So the only force acting here is the spring force. The generalized spring force can be written here as F, which is a function of x position, to be equal to minus some constant k1 times x plus some constant k2 times x squared plus some constant k3 times x cubed plus the higher order terms. Well, this might not look very familiar to you. What about this formula? Fx equal to minus kx? Well, this is the Hooke's law, which you are familiar with, right? But not the one above. Well, actually, the above equation, this one, is the more generalized equation of force acting on a spring, where x can take any value. This one is actually valid for small displacement. So that means for small displacements, we can ignore these higher order terms, and then we can call this motion a simple harmonic motion. There is an alternative form of writing this thing, which is force is proportional to minus the displacement. This is also known as the Hooke's law. Now let's try to find out the differential form of this equation. Okay, so we know that F is equal to ma, the Newton's formula. So it is equal to minus kx. And what is acceleration A? Well, it is the second derivative of x with respect to time, right? So this is again equal to minus kx. And now this time derivative, the second derivative, we can write it like this. This is a short notation which tells us that it is second derivative of x with respect to time. Okay, so mx double dot equal to minus kx. Now if we move this constant on this side, what do we get? Well, x double dot equal to minus k over m times x. Okay, so now let's take all those things on the left hand side. We get x double dot plus k over m times x to be equal to 0. Now, what are these K and M? Well, K is the spring constant, which is the strength of the spring. And what is M? Well, M is the mass of that object, right? So they both are constant. So that means we have a constant term here, which we can rewrite for some reason, which we'll explain later, as omega squared. Okay? So we have defined here omega to be the square root of K over M. So this is our equation for simple harmonic motion. As you can see, this is a differential equation. Well, actually it is a second order linear homogeneous differential equation. And what do we mean by that? Well, I will add a link to what differential equations can be classified as. Okay? That means what do we mean by homogeneous, second order, and linear. Okay? Now we can say that simple harmonic motion is a motion which can be stated or expressed by this equation. Now, let us take a different view of this. So, as we can write down f to be proportional to minus x, from this we can write down a to be proportional to minus x as well, because you see m is a constant and f equal ma, right? So acceleration is actually proportional to the displacement with a minus sign. So here what it means is that the acceleration of this movement is not constant. It depends on the displacement, and the larger the displacement, the higher the acceleration. Okay, they're proportional. But the minus sign indicates that the direction of acceleration, or even the direction of the restoring force here, is opposite to the direction of displacement. Now let us have a closer look at this definition, f equal minus kx. So here you can see that this object is oscillating around this equilibrium position. Okay, and this is its maximum displacement. Okay, so as the displacement is increasing, as you can see, the force is also increasing. But look at the sign of the force. It's opposite to the sign of the displacement. That means when the object is going in this direction, just wait, okay, so it is going in this direction, the force is acting in the opposite direction. You can see it here, okay, and same happens here, okay.